All right, so for this lesson, we're going to utilize all of our techniques that we've learned in the past, meaning we're going to utilize our power rule, our product rule, our quotient rule, our chain rule, all of our exponents, logs, and trig rules. And we're going to see what happens when we've got x's and y's intermixed, and we don't want to have to separate them like we've seen in the past. Every question we've seen so far, it's been y equals something in terms of x. What we're going to do now is we're going to see, what about the functions where x and y's are all intermixed, like circles or crazy hyperbolas? What do we do then? And what do we do when we've got x and y's and there's no way for us to separate nicely? So it's called implicit differentiation. And the fun thing is that you've been doing it all along. But I'm going to show you how to do the technique on a question that you already know how to do, and then see how it's utilized in more complicated questions. The most important thing that we need to know about implicit differentiation is that we tend to use it when x and y are intermixed. We don't want to break them apart, or we just can't break them apart. Here's the rule. We're going to take the derivative of every variable, x and y. We're going to take its derivative using our power rules and so forth. But when we take the derivative of the y, we're going to multiply by dy dx. You've already been doing it, you just didn't realize it. So here's the first example. We have y equals x squared. Right now, y and x are separated from each other, and we have a function of y with respect to x, like we've always seen. But we're going to use our technique about implicit differentiation and say, well, what do? We're going to take the derivative of every variable we see, but when we take the derivative of y, we're going to multiply by dy dx. So here we go. Let's focus in on the y. Right now, y has the exponent of 1. So what we're going to do is we're going to take the derivative of y, and we're going to say, bring the 1 down, and we're going to multiply by dy dx. Now, again, do you ever need that 1? No, but we took the 1 down, decreased the exponent by 1, which is 0. That's why we don't see y to the 0. And we're going to multiply by dy dx. Well, on the other side of the equal sign, we take the derivative of x. Well, that's just 2x. We don't need to multiply by anything because this function is a variable with respect to itself. Again, we're looking for the derivative of y with respect to x, so this would be the derivative of x with respect to x, which wouldn't make any sense for us to write. So let's look again at another one. What happens if I had y equals the sine of 3x? Once again, we know how to do this, and what's nice about this function, y is separate from x right now. But we're going to, again, play along with the idea that we're going to take the derivative of every single variable, but whenever we take the derivative of y, we're going to multiply by dy dx. Once again, y has an exponent of 1. We're going to bring them down. And we're going to decrease that exponent by 1. Again, y to the 0, anything to the 0 power is 1. That's why we don't write it. But we just took the derivative of y. If we take the derivative of y, we must multiply by dy dx. So there, we have the derivative of y. So this is y to the first power. And now let's take the derivative of the sine function. Once again, this is our M&M idea. Take the derivative of sine, which is cosine, keep the angle, and now multiply by the derivative of the angle, which is 3. What we have is dy dx equals 3 cosine 3x. We're just so used to saying that y turns into dy dx. That's because when you take the derivative of y, you're actually taking the derivative of that variable. The derivative of y is just 1 times dy dx, because you have to make sure you specify that you took the derivative of a y variable with respect to an x variable. So what happens when x and y's are intermixed? Here we go. X squared plus y squared equals 4. This is a circle centered at the origin, radius 2, all the way around. We have a choice. As of this moment in time, x's and y's are on the same side. We can't do this problem for the value that we know how to do it. If we're so used to having y by itself, we absolutely can do that. We can get y by itself and then take our derivative. And I'll show you that. And then I'm going to show you how implicit differentiation makes things so much nicer. So, method 1. We're going to get y by itself. So the first thing I'm going to do is I'm going to subtract the x squared. So we have y squared equals 4 minus x squared. Well, now I've got to get rid of the square, so I need a square root. If I take the square root of both sides, that means I need a plus or minus. So we have y equals plus or minus the square root of 4 minus x squared. So now we've isolated the y, and we're left with a function that has only just x's on the right-hand side. However, if I'm going to take the derivative this way, I have to recognize that y equals the positive square root of 4 minus x squared, or y equals the negative square root of 4 minus x squared. I've got to treat both of them differently. And then I'm going to have to turn this into a chain rule by saying, okay, y equals 4 minus x squared to the 1/2 power. Take the derivative of a chain rule, and I'm going to have to do it again over here with the negative, and 4 minus x squared to the 1/2 power. That is a lot of work, and I haven't even begun to even take a derivative yet. All I've done is just simplified the problem so I can take a derivative. There's got to be a better way, and there is. Not doing method number 1, meaning not trying to get y by itself on one side of the equal sign, everybody else on the other side. Let's leave it the way it is and just follow the rule. Take the derivative of every variable, but when you take the derivative of a y, just multiply by dy dx. All right, method number 2. Let's do implicit differentiation. So here we go. We have x squared plus y squared equals 4. Let's take the derivative of x squared. The derivative of x squared is 2x. Now, it was an x, so I don't need to multiply by anything. Let's go to the next term. The derivative of y squared would be 2y. We just bring the exponent down and decrease it by 1. Seems pretty easy so far. But we have to remember that we just took a derivative of y. And if we take the derivative of y, we're going to multiply by dy dx. So here we go. I'm multiplying that term by dy dx. Equals, what's the derivative of 4? Just a number, so it's 0. So far, I've now actually taken a derivative. In method number 1, I haven't even yet to begin to take a derivative, and I've got to do way more work. So, am I done? No, you have to isolate the dy dx. That's not going to take us very long. So the first thing I'm going to do to get dy dx by itself, because that's the whole point of these problems, is to find what the slope is. What's the derivative? Get dy dx isolated. Let's subtract the 2x. So 2y dy dx equals negative 2x. Well, let's divide by 2y. Dy dx equals negative 2x divided by 2y. Can we simplify? Sure. The 2's cross out, meaning the derivative is negative x over y. That's very interesting. What we're seeing is that for the very first time, that a derivative equals a function of x and y. And that's because the original problem was a function of x and y intermixed. So we can leave them separate, and we can take the derivative of two things, and it's going to be crazy and messy and all this algebra and extra work, or we leave them the way they are and get a function where x and y's are still intermixed. We can still plug in values for x to get y and so forth, but it's so much nicer and cleaner for us to use. So, what do we do when x and y's are intermixed? Leave them and take the derivative of every variable that you see, but whenever you take the derivative of a y, you just multiply by dy dx. So let's do another example. Okay. Again, this is a circle, but knowing that it's a circle is not important, but it is a conic section. But it's a circle, but it's not centered at the origin anymore. So, are we going to try to get y all by itself? I hope not, because I don't even know where to begin. Am I going to have to actually complete the square? We learned that in Algebra 2. I hope I don't have to do that again. And we don't. We're just going to leave it exactly the way it is. And we're going to take the derivative of every variable that you see. But when we take the derivative of y, let's multiply by dy dx. The derivative of x squared, 2x. The derivative of y squared is 2y dy dx. The derivative of negative 2x is negative 2. The derivative of 3y is 3 dy dx. Equals the derivative of 8, well, it's just a number, it's 0. We have successfully taken a derivative. We've taken the derivative of every single variable we see, so y squared became 2y, but we didn't forget to multiply it by dy dx. The derivative of 3y is 3, but we didn't forget to multiply by dy dx. Now, we're not quite done. Our job still is to get dy dx by itself. So what we're going to do is we're going to keep anybody that's got a dy dx on the left-hand side and move everybody else that doesn't have a dy dx to the right-hand side. So we're going to keep 2y dy dx plus 3 dy dx on the left-hand side. And we're going to move everybody else to the other side. So that means it's negative 2x plus 2. Now, again, our job is to get dy dx by itself. This is a really cool technique. We've gotten the dy dx all by itself, but we need to pull it out because we need to get rid of this 2y and that 3. They both have a dy dx in common. Let's factor out. So if we factor out a dy dx, we're then left with 2y plus 3. And again, if we distribute it back in, we come back right where we started. Equals negative 2x plus 2. The last thing I'm going to do is just divide by that quantity. So dy dx equals negative 2x plus 2 divided by 2y plus 3. I've found my slope, my instantaneous rate of change, and it's a function in terms of x and y because I started with a function of x and y. Again, all I'm doing is leaving it the way it is, not trying to resolve for y by itself, but every time I take a derivative of a y, I'm just going to multiply by dy dx. Once I do that, I'm going to isolate dy dx on the left-hand side, everybody else to the other side, factor out, and then divide by the quantity. It's a very similar pattern over and over and over again. Now, that's as complicated pretty much as it gets. So how can we make this harder? When we start mixing in product rules, quotient rules, chain rules. So let's look at a product rule with x and y. Okay, what we have is x squared plus xy plus y squared equals 10. There is no way for us to simplify this problem without some other level of mathematics, linear algebra, to get rid of the cross product term right here. So there's no way for us to really break it apart. We're going to leave it exactly the way it is, and we're just going to treat that as a product. And we're going to multiply by dy dx anytime we take a derivative of a y. Not so bad. Here we go. The derivative of x squared, 2x, plus what you see here is x and y. It's a product. X is first, y is second. So x is first, y is second. So as long as we remember our product rule, first derivative of the second plus the second derivative of the first, we should be good to go. So I'm going to put this in big parentheses to show you what I'm doing for this term, okay? So it's the first x times the derivative of the second. The derivative of y is 1. but then we need to multiply by dy dx. Plus the second y times the derivative of the first, the derivative of x, is 1. So what we've just done is we've taken the derivative of x and y as a product and left them like that. First times the derivative of the second, plus the second times the derivative of the first. Now let's go to the y squared term. Well, the derivative of y squared is 2y, just bringing the exponent down and decreasing it by 1. But we're going to not forget to multiply by dy dx. What's the derivative of 10? 0. So what we've done is we've simplified our problem by just leaving it the way it is and just taking the derivative of each term separately. Now, our goal is to get dy dx by itself. So let's clean this up and then we can start moving things around. We have 2x plus x dy dx plus y plus 2y dy dx equals 0. We need to get dy dx by itself, so we're going to keep all the dy dx's on the left. Everybody else is going to the other side. So we have x dy dx plus 2y dy dx equals negative 2x minus y. So once we've done that and got all the dy dx's on one side, let's factor out a dy dx. If we pull out a dy dx, that leaves me with x plus 2y in parentheses on the left-hand side equals negative 2x minus y. The last thing I need to do is to get dy dx by itself is divide by that quantity. So dy dx equals negative 2x minus y, all divided by x plus 2y. We've kept our function in terms of x and y all intermixed, taken the derivative of every single variable, not forgetting to multiply by dy dx when we took the derivative of y, and clean it up. So how can we make it harder? Same idea, and also putting variables on the other side. (3x plus y cubed minus xy equals x squared plus y to the fifth minus 13x. So we have 3x plus y cubed minus xy plus x squared plus y to the fifth. You know what? I'm going to change this just a little bit to negative 13x to the 10th. That way we're keeping everything a little bit different and a little bit separated so we can't move one over. So here we go again. 3x plus y cubed minus xy equals x squared plus y to the fifth minus 13x to the 10th. I do not want to simplify it and try to get y by itself. I'm going to leave everybody the way it is. I'm going to take the derivative of every single variable. I'm going to take the derivative of y. I'm going to multiply by dy dx. But I need to be aware of the one little part that's going to be really tricky and sneaky. And it's right here. Again, it's that product term. This product needs to be taken carefully when you deal with the x and the y. So just keep them separate right now in your brain that when I get to it, it's going to be a product rule and I've got to slow myself down. Here we go. The derivative of 3x is 3. The derivative of y cubed is 3y squared. Beautiful. But I just took the derivative of y, so I'm going to multiply by dy dx. Minus, I'm about to hit the product. So if I'm about to hit the product, I need to make sure that I know that this guy is the first and this guy is the second. I'm going to put it in parentheses because I can't forget that I'm going to have to distribute a negative eventually. So let's keep them in parentheses. So again, if I've got this xy product, it is the first x times the derivative of the second. Well, the derivative of the second is 1 dy dx plus the second y times the derivative of the first. Well, the derivative of x is 1. What I've just done is I've taken the derivative of the product, I've kept them separate, and I didn't forget to distribute the negative. Equals the derivative of x squared is 2x. The derivative of y to the 5th is 5y to the 4th. We have to remember dy dx. And the derivative of negative 13x to the 10th would be negative 130x to the 9th. We have successfully taken a derivative of every single variable. We took a derivative of y, we multiplied by dy dx, and we successfully handled the product. What we gotta do now? Get all the dy dx's on one side, everybody else on the other, factor, simplify. So what side do we want them on? They tend to always go to the left-hand side. So let's get all the dy dx's on the left-hand side. Let's first take care of this parentheses, and then we can start shuffling around. 3 plus 3y squared dy dx minus x dy dx minus y. Again, I'm distributing. Equals 2x plus 5y to the 4th dy dx minus 130 x to the 9th. So I've simplified. Now let's get everybody where they need to be. I need to get this dy dx on the left-hand side, and I need to get these two terms on the right-hand side. So let's do the shuffle. We have 3y squared dy dx minus x dy dx minus 5y to the 4th dy dx. Again, I subtracted him over. Equals 2x minus 130 x to the 9th, because they were already over here. Let's bring the other two terms to the right-hand side, so minus 3 minus y. We have moved all the dy dx's on one side, everybody else came to the right side. Once we've done that, we can now see if they all have a dy dx in common. Let's factor it out. If I pull out the dy dx, that leaves me with 3y squared minus x minus 5y to the 4th equals 2x minus 130x to the 9th minus 3 minus y. Last step, divide by the quantity. So 2y dy dx equals 2x minus 130x to the 9th minus 3 minus y, all divided by 3y squared minus x minus 5y to the 4th. So I've walked us through all of the steps that you would need to take. Do you have to show all of your work all of the time? Well, if it's multiple choice, absolutely not. Once you get to here, you're going to see that you're going to factor out and then divide by the quantity, so you can just jump to that step. However, if it's free response, meaning you have to show your work for everything, you need to show your steps, especially the factoring portion. This little step right here is worth a point all by itself, besides just getting to the answer. So this part, the derivative of the very first line, you showing that you factored and arriving at the right answer, are all numerical values in terms of our point system and how to grade. So if it's multiple choice, you don't have to show all of your work. That's so fine if you kind of skip some steps and get to the final answer, that's okay. But if it's free response, please make sure that you slow yourself down and show all of your work, because we're looking for it. It's the process that we're looking for. So we've just talked about implicit differentiation. We've talked about products. We've talked about variables on both sides. Let's throw some trig in there, because that's also where you're going to see it. Okay, what we have is we've got a trig function, and oh no, the angle has x and y intermixed. There is no good way to get the y by itself. So I'm not going to try. I'm just going to leave him exactly where he is. And when we get to taking his derivative, we're just going to multiply by dy dx. So here we go. Again, the trig functions are our chain rule. We can't get to the angle until we deal with the trig. So let's deal with the sign. The derivative of sine is cosine. So we've got cosine of the angle xy. Now that I've dealt with the trig portion, let's go and investigate the angle. The angle is a product. What do? Well, let's make sure that we treat it like a product the way it's supposed to be. We have the first and the second. The first is x, the second is y. So the first, x, times the derivative of the second, the derivative of y, is 1 dy dx. I'm just going to write dy dx. Plus the second, y, times the derivative of the first, which just so happens to be 1. What we've done is we've taken the derivative of the trig and we're about to multiply by the derivative of the angle. If we recognize there's the angle. So it's a product. Equals. What's the derivative of x? 1. We have successfully taken a derivative. Taken the derivative of the trig function, kept the angle untouched. Then we multiplied by the derivative of the angle. The angle was implicit differentiation. X's and y's intermixed. We took the derivative of that product and we didn't forget to multiply by dy dx when we took the derivative of y. Now, the hard part necessarily begins. We've got to get dy dx by itself. There are several ways that we can do this. We can divide by cosine xy over to the other side, and then we can subtract the y and then divide by x, or we can distribute the cosine xy. I'm going to show you both of them because I'm not sure what you're going to encounter on the multiple choice portion of your test. So let's see different techniques and how to deal with it. So if you ever encounter a question like this, which you probably will, what do? So one way of simplifying. Let's divide by cosine of xy. So what we've got is x dy dx plus y equals 1 over cosine of xy. Now, the second thing I'm going to do is I'm going to subtract the y to the other side. And I get x dy dx equals 1 over cosine of xy minus y. Then I'm going to divide everything by x. So dy dx equals 1 over cosine of xy minus y, all divided by x. Now, that looks kind of gross. We've got crazy complex fractions going on. I'm not so sure I like this so much. So this is a perfect answer. However, I know that you're going to probably be having to switch one thing to make it more simplified. What I want us to focus on is right here. 1 over cosine xy. He's the one piece of this whole answer that doesn't look like he fits correctly. He's causing us a little bit of heart palpitations. We don't know exactly what to do with him. So let's change him using a reciprocal identity. 1 over cosine xy is the same thing as secant of xy. So here we go. We can change this to say secant of xy minus y all over x. This exact question with this exact answer appeared on an AP exam multiple years ago. So great test question. So what happens if you didn't go this route? What was another way of actually simplifying it? Well, another way of simplifying was to actually take the cosine of xy and distribute him in. So let's look at the other way of simplifying this problem. I'm just going to rewrite it really quickly. Cosine of xy times x dy dx plus y equals 1. I can take this cosine of xy and distribute him in. When I do that, I get x cosine of xy dy dx plus y cosine of xy equals 1. Again, all I did was I took this guy and brought him inside to both of those terms. So now what am I going to do? The same thing I've done before. I'm going to move this value to the other side, and then I'm going to divide by that coefficient to get dy dx by itself. So I've got x cosine of xy dy dx equals 1 minus y of cosine of xy. And then I'm going to divide by this quantity, and I get dy dx equals 1 minus y cosine of xy, all divided by x cosine of xy. That's also a perfect answer. But do you agree he doesn't look like that one? But they're exactly the same. So how can I get this, which is a beautiful answer, which looked just like this one, to maybe look like that one? Well, what do I know? I heart division. We know that the left-hand side and the right-hand side are treated the same because the bottom applies to both. So I'm going to break them apart and see if we can arrive at the same answer. So if I do that, and I erase up here so we can put some more work. Let's see what happens. What we have is dy dx equals 1 over x cosine xy minus y cosine xy over x cosine xy. So I heart division, the bottom applies to everything in the numerator. And what do we see? Well, do you agree he can flip up to become secant like we have over here? So that means I've got secant of xy over x. What about over here? What I recognize is, oh, cosine xy cross out. That leaves me with negative y over x. Well, they now have the same denominator still once again. That gives me secant of xy minus y all over x. Same exact answer, doesn't matter which way you go. So please keep that in mind. There's no one or right or wrong way of approaching it. But again, great test question, because not only do you have to deal with the trig, you got to deal with the product, you got to deal with the y and the x all intermixed, implicit differentiation, and then getting to a final answer of simplification in terms of recognizing, well, what does cosine do? Cosine can flip and become a reciprocal. What can I do to get x by itself? How can I clean it up? So let's maybe do another one. All right, so what do? When we've got trig, we've got logs, and we've got x's and y's everywhere. Well, let's take implicit differentiation. We take the derivative of every variable, but we multiply by dy dx, and we take the derivative of y. The derivative of sine is cosine. The derivative of the angle is 1 dy dx. So here we go. The derivative of sine is cosine. Keep the angle untouched. Now we expose the angle. The derivative of y is 1 dy dx. Okay, equals the derivative of cosine. Well, the derivative of cosine is negative sine. Again, the cos are negative. Keep the angle, sine of x. And now multiply by the derivative of the angle. Derivative of x is just 1. Minus. Well, we've got an ln. ln says we focus in on the function right here, xy. Ooh, it's a product, which means I'm going to have to remember that the x is first, the y is second. So it's the first x times the derivative of the second, dy dx, plus the second y times the derivative of the first, which is 1. There is the product of xy. Now, with the log function, what we remember is that we take the derivative of the function and then we divide by the function itself, which is xy, and then we multiply by ln of the base, which happens to be ln e. So again, we have a product, first derivative of the second plus the second derivative of the first, divided by the original function itself, because we're rewriting ln e. Once again, ln e wipes out, so we don't ever really have to write it. So we have successfully taken our derivative, but now it's our job to clean it up. Let's go ahead and simplify and make things a little bit easier. Do we agree that that's a monomial? And so we're just going to put it up front so we don't forget that he's there. So I'm just going to put the dy dx up here so I don't lose him. And it's the cosine of y. equals, well, 1's not bothering me, so it's negative sine of x. And then on this one, I'm going to basically distribute the negative, and I'm also going to keep the bottom separate as well. So we have negative x dy dx over xy minus y over xy. So again, I distribute the negative into the numerator, and our bottom, again, I heart division, goes to both. What do we recognize? Well, x's can cross out here, y's can cross out there. So let's go ahead and do that. dy dx cosine of y equals negative sine x, and then minus 1 over y dy dx minus 1 over x. So again, these x's cross out, so it's 1 over y, and these y's cross out, so it's 1 over x. Again, now our job is to get all the dy dx's on the left, everybody else on the right. He's got to move. We're going to add it over. So dy dx cosine of y plus 1 over y dy dx equals negative sine of x minus 1 over x. What are we going to do now? Factor out a dy dx. So we have dy dx times cosine of y plus 1 over y equals negative sine of x minus 1 over x. Last step, divide by that quantity, which means dy dx equals negative sine x minus 1 over x all over cosine of y plus 1 over y. Would we need to clean that up? Probably not. Because when it's kind of hard to simplify trig and logs, if it's all trig, we can do a little bit more work. That is a perfect answer. We have taken a derivative of x's and y's all intermixed. We've done it with trig, we've done it with logs, we can do it with exponential functions, we can do it any kind of functions. But as long as we remember to take the derivative of, when we take the derivative of y and multiply by dy dx, we'll never be wrong. Just slow ourselves down, especially when we deal with products. So we always have to make sure that we have the first and the second. So that walks us through implicit differentiation. We're going to really utilize this technique of implicit differentiation when we get into something called related rates. When variables, all variables, are changing with respect to time. So what do we do then when we're trying to calculate volume, area, what's happening when you blow air into a balloon? Everything is expanding at a rate of time. So we're going to utilize this technique